Alrighty, well, good afternoon. My name is Dmitry, and I'm here to present to you on setting the optimal temperature indoors to minimize your energy demand when using an enthalpy recovery wheel system, or an energy wheel. Okay, so the enthalpy recovery wheel system, what is it? Well, what it does is it increases the temperature of your air outside that's coming into your building before you have to heat it up anymore. Or on the contrary, it actually decreases that temperature before you have to cool it down any additional amount. And the overall purpose of it is to reduce the amount of energy that you need in order to reach that temperature indoors. And the way that it works is that you have your temperature of your air coming into the system, and you're trying to get this temperature to match your set temperature indoors. So somehow you have to change the energy to be able to do that. And what the enthalpy wheel does is that it takes that outdoor energy, that temperature, and it boosts it up a little bit before it continues down the path and then needs to be heated up additionally by the heating or cooling coils. And then the way that it does this, the way that the actual wheel works is that temperature, the air leaving the building, ends up contacting the enthalpy wheel on top and transferring the temperature. So the temperature from the air leaving contacts the temperature of the air coming in, and that's where you get that temperature differential. And then it just leaves the system. So my research question is, what is the actual optimal level, what is the actual optimal number to minimize this energy demand? And we're solving for T set. So we're assuming that the set temperature has to be between 16 and 26 degrees Celsius, between 61 degrees Fahrenheit and 79 degrees Fahrenheit. So reasonable temperatures for us to be able to feel comfortable. So the objective function is to minimize this additional heat required by subtracting the amount of energy that's being saved from the enthalpy wheel from the entire energy that needs to be applied. So using the equation for heat transfer, Q equals mc delta T, knowing the mass of the air, the mass flow rate of the air, and the specific heat of air, and the difference between the temperatures, you can calculate how much energy is actually required to accomplish this. So, and we're looking at an annual optimization. So we're actually summing this result for every hour in the year. So it makes 8,760 points for each of the variables. So in the end, it's about 26,000 variables that are being calculated each time. So here's what the annual optimization model looks like. So the constraints, one of the main constraints is that there's only 8,760 hours in the year. Okay, another constraint is that we have constants. So we're assuming the specific heat of air and also the density of air and standard temperature and pressure. The comfort constraints between 61 and 79 degrees Fahrenheit, or 16 and 26 centigrade. There's also an equipment constraint. So this blower over here is limited to about 20,000 cubic feet per minute, which is about 9.4 meters cubed per second. And non-negativity constraints. We're looking at the absolute values of the differences between the temperatures, and you can't have a negative flow rate. So that's our favorite constraint, of course. All right, so the model formulation. We're minimizing how much total energy we need to do this, where the maximum energy is proportional to the difference between your set temperature and the temperature coming in. So that if you did not have an enthalpy wheel, how much energy would you have to consume in order to get that up to your set point temperature? And the energy wheel savings, this one here. So combining it and making it looking all pretty, here's our final objective function. And there are subject to those constraints, as mentioned before. And so our ultimate objective for optimizing the system is to find out what is that set temperature indoors. What do you set your thermostat to? So in order to run this simulation, we need to get data from Web Control, and the Web Control is a database that provides us information for all the different technologies in this building. And the types of things that we're looking for is the outdoor air temperature for every hour, coming in, this guy right here. And also the temperature after it hits the enthalpy wheel. That's this one here. Then also we need to know the volume flow rate that's coming inside. And we have our variable set temperature for what we're actually going to be solving for. So running the simulation, we get a beautiful, was done in Excel. So we have lots of data. And it turns out that the optimal set temperature for last year is actually 66 degrees Fahrenheit, or about 16 degrees Celsius. So, and that gives us a demand of about 56,000 kilowatt hours of energy. So applying that to costs, we pay about $5,600 a year to heat and cool this building. Assuming it's at 10 cents a kilowatt hour. Cost was not incorporated into this analysis. However, it's interesting to think about its proportion. Now, so the annual savings from the enthalpy wheel is actually about 31%. So if we were to have this at the set temperature, we would actually be saving 31% on our energy bill, having it set at 66 for the entire year. So a sensitivity analysis that I conducted was I was trying to see how is the optimal temperature different for each month as compared to for the entire year, and how do the energy savings compare between those months. Yes, beautiful spreadsheet data. So it turns out that each month is actually significantly different than another. So in March, we actually want to send it at 61 degrees Fahrenheit, whereas in January, we want to set it at 78 degrees. So it seems weird, we're going to be here hot at 78 degrees, but under these parameters, that is the optimal set point. And the logic behind why you would want to set it at 78 degrees in January is because the air leaving the building is going to be at about 78 degrees. So it's going to be contacting that below zero temperature of air coming inside. So you really want to raise that temperature up. And in order to do that, you got to kind of go outside your temperatures. So, right, so through the sensitivity analysis, our optimal solution turns out to be 46,000. So we're actually saving an additional 17% more energy if we're varying the set temperature per month as compared to just setting it for the entire year. So it's a total energy savings of 43% for the entire system when you're varying the set temperature. So the results show that for the year, 66 degrees is the optimal temperature, and it saves us 31%. And this includes about 25,000 kilowatt hours. So we're saving about $2,500 a year under the set point annual simulation. But if we were to vary it, we're actually saving an additional 17% relative energy to the set point. So the conclusion is that it's better to actually vary your set point temperature for each month as compared to just set it and let it go. And also this has shown that the enthalpy wheel actually does work. From the data that's coming in, we're showing that, hey, this system indeed has been saving us a significant amount of energy and money. So research extensions would be to determine the relationship between the average outdoor temperature and your energy savings. So if we had a map, I know Laura's had a beautiful map of the climate regions. So if we knew where your average temperature in Rochester, it was 57 degrees or something, what is that limit for where you would want to install an enthalpy wheel? And then compare the performance of the enthalpy wheel system to the other enthalpy wheel system that we have at RIT, which was just installed in Institute Hall. So it would be interesting to see whether or not their system performs similarly to our system. And also, how would their enthalpy wheel perform on using our data in this building to see, to see their effective rate, and also to see the sensitivity between these types of systems. And also, the last thing we're going to do, so the enthalpy wheel here moderates the temperature, but we also have a dehumidification wheel over here, or a desiccant wheel, that models the humidity of the building. So the research extension would be to incorporate the energy savings from the desiccant wheel, the dehumidification wheel, and then figuring out what is the optimal level of set humidity in the building. Yes, that's it. Any questions?